So if somebody gives me the cue to start, I'll start. If somebody's doing an introduction, I'm not sure exactly how you're organizing your webinar, but please give me some sort of signal that I should start.
We're just waiting to few more people to join.
Okay, fair enough.
Start. Yes, sir.
Yes, please do.
Yes, sir. Yes, sir.
Good afternoon, Professor Dino.
Good afternoon.
I am Professor Somshekhar, Director of the institution.
Pleased to meet you.
We are highly honored. Welcome on board.
Thank you very much. Yes, I've been to your institute.
Yeah.
Yes.
Namaskar.
Thank
Namaskar. So, how are things at your end?
It's fine. I mean, we're all suffering from the COVID-19 effects of shutdown and lockdown and so on.
Okay.
Otherwise, things are fine, you know.
Okay.
It's raining at the moment and it's cold. It's about 13 degrees.
Okay. So what time is it at Glasgow?
It's 10 o'clock, just after 10 o'clock.
10 o'clock morning?
In the morning, yes.
Okay. Right. So I have to say good morning for you, and
yes.
for others it is
good afternoon to all of you, and good morning for me. That's true.
Yes.
Very good.
Good morning to Professor Dino, and good afternoon to all who have joined. And I think we'll be starting in a few seconds. I'm going to call my anchor, Dr. Nina. Dr. Nina, are you there?
Yes, ma'am.
Yes. Dr. Nina, I think, Director sir, are we good to go? Is everything okay? We can start?
Fine, please go ahead.
Professor Dino, you are settled, we can start?
Okay.
Professor Dino?
Should I just get started then? Okay.
Okay, so we'll start the introductory part. We'll call
Dr.
you.
Poonam?
Yes, sir.
Dr. Poonam, हमारा डायरेक्टर कोई ज्वाइन किए हैं? डायरेक्टर R&D?
No, sir. No, I don't think so. We sent them.
Okay. Then, just I wanted to take their name in case if they have joined it.
No, I don't think so. They have joined today.
Okay.
Let me check. I'll just let you know. Just hold.
Yeah, please check it and let me know.
Okay. So let me know when I can start, and I'll just start.
Yeah, definitely, Professor Dina. I'll give you a call. Okay.
I'll wait until you say
okay,
start.
Sir.
Okay.
Director sir, nobody has joined.
Okay. Go ahead.
Okay. Dr. Nina, you can start.
Okay. Well, first of all, I'd like to thank you all.
Professor Dino, we are asking your anchor to start.
Can I start?
You hold on. Okay. You hold on.
Okay. Thank you very much. Well, first
Shall
of all,
I start, ma'am?
Hello?
Ma'am, shall I start?
Yes,
Yeah, please go ahead, Nina.
Science is a way of life. Science is a perspective. Science is the process that takes us from confusion to understanding in a manner that precise, predictive, and reliable. A transformation for those lucky enough to experience it that is empowering and emotional. A marvelous good afternoon to everyone. On behalf of RKGIT, Ghaziabad, I, Dr. Nina Sharma, extend a very warm welcome to all the participants to the last session of International Webinar Series, Recent Advances in Science, organized by the Department of Applied Sciences and Humanities, RKGIT. I must begin with a note of sincere gratitude who joined us from the very first day of this webinar series, Recent Advances in Science. Today, we have a very interesting and interactive topic, new technologies based on laser plasma interaction. Our speaker of the day is Professor Dino Jaroszynski, Director, Scottish Centre for the Application of Plasma-Based Accelerators, University of Strathclyde, Glasgow, Scotland, UK. We welcome you, sir. Now, I request Dr. D.R. Somshekhar, Director RKGIT, to deliver welcome address. Sir, please, I over to you, sir.
Thank you, Dr. Nina. Am I audible? Dr.
Yes,
Nina?
sir.
Yes, sir. You are audible, sir.
Yes,
Thank
sir.
you. Thank you. Good afternoon, ladies and gentlemen. Honorable Speaker of the Day, Professor Dino Jaroszynski, Director, Scottish Centre for the Application of Plasma-Based Accelerators, University of Strathclyde, Glasgow, Scotland, UK. Group Director, the invited speakers, guests, convener of International Webinar Talk Series, Dr. Poonam C. Kumar, Professor and HOD of the Applied Science Department, Coordinator and coordinators of the program, Dr. Sanjeev Goyal, Professor of the Applied Science Department, and Dr. Pawan Kumar, Associate Professor of the Department, delegates from India and abroad, teaching fraternity from different institutions, complete parivar of RKGIT, students and friends. I deem this as my proud and privilege to welcome you all for the 5th and concluding international webinar talk series, which started on 4th of August 2020, organized by Applied Science Department, Rajkumar Goyal Institute of Technology, Ghaziabad. Friends, at the outset, let me welcome our Honorable Speaker of the Day, Professor Dino Jaroszynski, Director, Scottish Centre for the Application of Plasma-Based Accelerators, University of Strathclyde, Glasgow, Scotland, UK. Sir, in spite of your busy schedule, you made it convenient to be with us on virtual platform and to grace the concluding session of the webinar talk series. Sir, on behalf of the management, on behalf of the committed band of teachers, and on my own behalf, wholeheartedly welcome you, sir. I also take this opportunity to welcome all the invited guests, the speakers for the program. I also extend wholeheartedly welcome all the participants, complete RKGIT family, students and friends for this concluding session of the International Webinar Talk Series. Friends, I learned galaxy of speakers have discussed advanced topics in this webinar talk series and benefited more than 1,000 teaching fraternity. My humble submission to all of you is bring out some innovative researches, publications and projects, and which is in need of the above. Friends, then only our mission of India, that is Skill India, Make in India, Atmanirbhar Abhiyan, etc. is possible. Friends, it is not only the research. So one has to think of the collaborative learning also, which is also in one of the outcome-based education system. And of course, the pandemic of COVID-19 is giving an ample of opportunities to bring this collaborative learning even online platform also. I request all the faculty members, all the participants to bring out some way or the other. It may be in the field of research, it may be in the field of innovative projects, or it may be in the publications, or it may be in the collaborative learning, and so on and so forth. Friends, you also aware, last week, our Honorable HRD Minister made an announcement from 2021, the eligibility for the faculty to teach the university students, the PhD is a must. So please, the faculties who have not acquired the PhD qualification, so please think in very serious and see that they also equip with the required PhD degree to become university professors. Friends, science is so important. You cannot breathe, you cannot drink, and you cannot live without science. So such is the importance of science, my dear friends. I congratulate the department for organizing such a wonderful international webinar talk series. I wish all the success of the program. Thank you very much. Jai Hind. Over to Dr. Nina.
Thank you, sir. Now I would like to request Dr. Sanjeev Goyal, Professor Applied Science and Humanities, to introduce the speaker of the day.
Okay, thank you, Dr. Ninaji. Let me introduce speaker of the day, Professor Dino. Professor Dino Anthony Jaroszynski was born in Finland in 1955, grew up in South Africa and settled in the United Kingdom in 1977 to complete his studies. He was awarded the first degree in physics and a PhD from the University of Manchester. He worked as a research fellow at a number of well-known European laboratories between 1983 and 1996 before taking up a permanent position at the University of Strathclyde, Scotland. He comes from a family of artists which has inspired an interest in the medium of art as a language of science. Professor Dino Jaroszynski is a plasma physicist and is a fellow of the Royal Society of Edinburgh, FRSE, and the Institute of Physics. He is the founder director of Scottish Centre for the Applications of Plasma-Based Accelerators, where he uses high-power lasers and plasma as a compact radiation sources. Professor Dino's main research activities have been in the area of collective radiation matter interactions in atomic systems, free electron-like devices, and more recently in plasmas. His research has major implications for the development of the next generation tunable X-ray and far infrared sources and the next generation of ultra-high intensity lasers. His research has major implications in these areas too. Professor Dino published more than 300 research papers in highly reputed journals like Nature, Physical Review Letters, and Sciences, etc. Professor Dino is principal investigator and co-principal investigator of 48 projects, including famous project Lab in a Bubble. Now I request Professor Dino to enlighten us with knowledge sharing on new technologies based on laser plasma interactions. Please, sir.
Well, thank you very much for that great introduction. And thank you all for inviting me to give this webinar, this seminar. And it's a great privilege for me, and it's nice to see some good friends on the list of participants. And of course, I visited your institution and enjoyed very much my time there. And of course, my friend and collaborator Pawan Kumar is always been very, very friendly and supportive, and you know, contributed to me enjoying being in India. And actually, for me, India in many ways is like a little bit like a second home, because I feel when I go there, I always feel at home and always very welcome. So, but today I'm going to talk about science, and particularly about the medium of plasma, which is fully ionized gas, and how to harness the plasma, the strong fields of plasma, to do some useful work. And so what I'm going to show you in the next series of slides is how we can use high power lasers to separate charge in plasma, to use the forces of the high power laser pulse. These are very high power. You're talking about powers up to terawatt levels, several terawatt, even a petawatt level. And at for those high powers, if you focus the laser pulses to a very short, let me just, 1 minute, I'm going to see if I can, I need somehow to, 1 minute, for some reason I don't have access to my slide show. Oh, there we are. Okay, so I've got it now. Okay, so and just to give you a little bit of some sort of perspective of where I am, what I'm doing, I'm going to start a little bit with the physical environment and a little bit historical history of what I do. Let me just make sure that I'm not getting a message. Okay, saying everything's fine, so you can hear me. Anyway, so I'm situated in Scotland, Scotland is in the north of the United Kingdom, and it is a country which has had a great tradition in education and in science and in culture in general. And some of the very most famous scientists have come from Scotland, in fact. You know, somebody who's very important in the field, in our field, is James Clerk Maxwell. He was born in Scotland, in Dumfriesshire, which is just south of Glasgow. And he proposed a set of equations which is now used as the basis for quantum mechanics, for the study of light, and also for understanding the propagation of light and the interaction of charged particles with electromagnetic fields. And also James Hutton in the early 18th century shows, we're looking at the geology of the Earth's crust, the structure of the geology. He was able to show that the world was much, much older than hitherto, at that time considered. And also the mass of the world was measured just north of where I live, on a mountain called Schiehallion. They looked at the deflection of a pendulum through the gravitational attraction of this mountain to the pendulum. By measuring the deflection, they were able to measure the mass of the mountain and also the mass of the world. Anyway, but Scotland has many universities, and 7 of these universities have linked together to make an alliance called SUPER. It's a physics alliance. It's the largest alliance in the country, in the UK, and it consists of 8 Scottish universities, and we are part of it. University of Strathclyde is one part of that. So, and we're in Glasgow, which is in the central belt of Scotland. It is the biggest industrialized area of Scotland. So today I'm going to talk about how one can use plasma as a basis for technologies. I'm going to basically concentrate on two main topics. One is how to accelerate particles using the electrostatic fields of plasma. Plasma is fully ionized gas. And by separating the charge, you can produce very large electric fields that can be up to a teravolt per meter. So in principle, if you could impose the acceleration field on a charged particle for a few meters, you can accelerate particles to the energies that you would get in an accelerator like the ones at CERN, the collider in CERN. But what I'm going to be focusing on is something very much smaller than that. And you can see the picture on the right. That is a few GeV accelerator. And I'll also tell you a little bit about how one measures the energy of an accelerator. But what I'm going to show is that by using plasma, one can miniaturize accelerators. One can reduce the accelerator sizes by factors of 1,000 or even 10,000. And this means basically you can make them more widely available, and you can explore new ways of new types of technology, which is based on these very, very miniaturized accelerators. Because the electric fields in the accelerator are so high that they also, not only are they accelerators, but they're very strong radiators of electromagnetic energy. And you can also take these charged particles out of the accelerator and you can pass them through devices like undulators. These are devices which you have in synchrotron sources which produce X-rays. So you can use the laser-driven accelerators in the same way as you use a conventional accelerator, with the benefit of having it very much smaller than a conventional accelerator. And not only that, but as I mentioned to you, you can also, the fields are huge in a laser-driven accelerator. You can use those fields also directly to produce electromagnetic radiation. So I'm going to tell a little bit about the ion channel laser. The ion channel laser is a way of harnessing these fields in the accelerator to produce coherent X-rays or ultraviolet light. And finally, I'm going to introduce you to how we can use the plasma, the waves generated in plasma using laser pulses to amplify light. In other words, basically to convert one form of light into another form of light, into, for example, a long pulse into a very short pulse, high energy pulse. And this can be considered as a type of amplifier. So I'll get to that towards the end of my talk. But first, I'm going to talk to you about conventional accelerators. Now, we all know the Large Hadron Collider. Large Hadron Collider can produce charged particles, protons, at about 7 TeV. So that is basically the kinetic energy that a particle will have after traversing a field, an electric field, over one of 7 tera electron volts. So you're talking about 10 to the 15 volts. Okay, so that's how you measure energy in an accelerator. You can just you consider its energy after it passes through a potential difference and gains the kinetic energy from traversing that potential difference. And these accelerators, like CERN, are very large because the accelerating strength of the accelerators is rather limited, because the cavities, and these are normally microwave accelerators, the cavities can only withstand a certain amount of field and power, and you cannot go above this power because the cavities break down. So that means that the cavities have a relatively small accelerating gradient. So at CERN, the gradient in 27 kilometers is about 7 megavolts per meter. Now, we also have, this is a circular device, so you have magnets to keep the particles on a circular path. You also have linear accelerators. So there's one at SLAC, this is in California. Now that is a linear accelerator, which has accelerating cavities in the same way as you'd have at CERN. So somebody's writing on the board, by the way, so just, these accelerators linear accelerators are basically the same type of accelerators as circular accelerators. The only difference there is you don't have magnets to bend the particles into a path. So so anybody who's writing on the thing should maybe stop writing on that, because I can't see my slides. I'll have to stop sharing and start sharing again. So okay. So let me see if I can. I'll stop sharing and start sharing again. Hang on a minute. So you have a linear accelerator, which accelerates particles to high energy. And these are very expensive devices because of their size. And the accelerating gradients, which are limited to about 100 million volts per meter. And these type of accelerators consist of radio frequency cavities. These are metal cavities, which are filled with microwaves. And by arranging the oscillation phase of the electromagnetic waves trapped in these cavities, one can ensure that the particles that traverse these cavities always see a positive acceleration field, and therefore they accelerate through these cavities. But if you fire a high-power laser into a plasma, and a plasma is fully ionized gas, you can separate the charge of the plasma. And the plasma has a tendency to restore itself to its original position, to a neutral environment. And the particles in the plasma will oscillate locally at something called the plasma frequency, which is determined by the density of the particles, the charged particles in the plasma. And if you fire a laser pulse through it, or even a charged particle through plasma, a bunch of particles, one can excite these plasma oscillations, and they will produce a structure which is like a wake behind a boat. So it's a structure similar to the wake behind a boat, which then has a very, very large electric field. So you separate the charge, and you separate it not only, you separate it, but in addition, you also separate it at a speed which travels along at the speed of the particle or the laser pulse that's perturbing the plasma. And that means that you make a sort of traveling wave structure. So that means it's perfectly suited to accelerate charged particles, because charged particles, when they get to high energy, will be traveling very close to the speed of light. And if you use a charged particle traveling along the speed of light, or a laser pulse traveling along the speed of light, excite this pattern, you will track the charged particles that you want to accelerate. So you'll see in the lower figure there that I show you, regions here where there's a large field where these particles can accelerate. The plasma can accelerate the charged particles. So, and just to give you some idea of the scale of these lasers, to be able to get these forces, one needs very high intensity lasers or high power lasers. You need lasers which are above a few tens of terawatts, and maybe even up to a petawatt of power. If you take these laser pulses and you focus them down to a small spot, much smaller than the breadth of a hair, one can produce intensities which are so high that any charged particle in the electromagnetic field of the laser pulse will be moving at the speed of light. So that also means that the plasma will change its optical properties. And this makes the plasma very nonlinear in terms of its interaction with the laser pulse. Okay, so just to give you some idea of the scale of the power, total power, the world usage is about of the order of a few terawatts. And the lasers we're talking about have more power than the total world usage of the power, but of course only in a very short time. So it means that the energy in the laser pulse is small, several joules at the most, maybe 100 joules if you up at petawatt powers. But it means that you have you can apply these very high powers, focusing them to produce intensity, very high intensity fields for a few cycles of the electromagnetic field. So this is normally of the order of about between 20 and 30 femtoseconds. So femtoseconds is about 10 to the minus 15 seconds. Okay. So and the other aspect of, or the other important point here is that we are dealing with media, with plasma as a medium. This is the primordial medium of the universe, of the visible universe, forms the most part. So what we do is we take either gas or solid matter, and we ionize the matter to make a fully ionized gas, and that is plasma. And the sort of media we use are gases, something like hydrogen or helium normally, and these are basically gases that fill capillary tubes or fill little gas cells. And if you focus a laser pulse into the gas, the laser pulse intensity is so high that it fully ionizes the gas. So what you're always dealing with in these situations, even if you start with gas, you're dealing with plasma. And you'll notice here in the top left-hand figure that you'll see a long filament. Now, what that means is that if you focus a short laser pulse to a small spot, it will diverge away very quickly. And the Rayleigh length, that's the length over which the laser pulse is intense, is rather short. You're talking about, a millimeter or a few millimeters. But because the laser pulses are so intense, and the plasma electrons oscillating in the field of the laser pulse are relativistic, they're traveling along at the speed of light or very close to the speed of light, they change their mass, and then change the optical properties of the plasma. So what happens there is the plasma starts to become like an optical lens, which depends on the intensity of the laser beam in the plasma. So what happens, you get self-focusing of the laser beam, and rather than diffracting away, you will get it guiding over a long length. So that's 4 centimeters on the top left. There is a few millimeters on the top right-hand side. And these are just gas. In this case, it's a gas jet. Here, it's a gas cell. And you can also use a capillary. And there we can use a capillary. If we want to pre-ionize the gas, we can, in this case, we fill it with hydrogen, we pre-ionize it with electrical discharge, and you can use that as a medium for these accelerators. So if you focus a laser beam into the plasma, you expel the electrons from the region where the laser pulse is, and you basically evacuate the plasma. The laser pulse travels along at its group velocity in the plasma, and that basically means it's the velocity at which the energy of the laser pulse travels in the plasma, which is slightly less than the speed of light, and you have trailing behind it the structure. And this structure, this wake structure, as you can see here, is just an evacuated bubble. In fact, you get a series of bubbles, and this evacuated bubble has very large fields associated with it. Now, this was first proposed in 1979 by Toshi Tajima and John Dawson, and it took until 2004 before this was demonstrated experimentally. Our team was one of the teams that demonstrated this for the very first time in 2004. So it was a very big breakthrough, and this basically laid the groundwork for making these accelerators into a technology that you can actually use for useful use. So you can see here the laser pulse travels along at its group velocity, a little bit less than the speed of light, leaving behind it the structure, which looks a little bit like that in the top right. But this is a simulation which shows it, and that's a three-dimensional plot there in the bottom right-hand side. So, so this is a very large electric field, and because they're traveling along at close to the speed of light, if you take a charged particle and you insert it into this accelerating structure, the particle will experience the field of the bubble, you know, the wake, so to speak, and it will accelerate just like a surfer surfing on a wave will accelerate on the wave. The particle will gain momentum from the wave, from the accelerating structure, and gain momentum, and its velocity will increase slightly. And in fact, at some point, the particle or the surfer will outrun the wave. That basically sets the limits to the length of the accelerator. So it means that you have to really think very carefully about how you structure these accelerators and how long you make them, because they only last, the available accelerating field only lasts for a short time, because the laser pulse is traveling along at a speed which is less than the particle's speed, and the particle will outrun the accelerating structure. It will go to the middle of the accelerating structure and then stop accelerating. So this means that it will reach a fixed energy. And this, in an accelerator, the electric field in volts per centimeter is just the elementary charge times the square root of the density of the particle in centimeters, in cubic centimeters. So, and this turns out to be up to 1 teravolt per meter. So this shows you that you can make a very, very intense field, or strong field in the plasma, just by focusing the laser beam into the plasma. So, and if you compare this to conventional accelerators, which have 100 million volts, so this means that these laser-driven accelerators are at least 1,000 times or 10,000 times a higher field than in a conventional accelerator. And just to, before I go on, just to say that I will quite often talk about, when I talk about the energy of the particle, I will talk about its Lorentz factor. Now, the Lorentz factor, this is from Einstein's theory, is just 1 over the square root of 1 minus the velocity squared of the particle over the speed of light squared. And it turns out that the laser pulse, you can associate a Lorentz factor with the laser pulse, and that's just the ratio of the frequency of the laser pulse to the frequency of the plasma oscillation frequency. And the maximum energy that you can accelerate to the particles to is just equal to twice this Lorentz factor associated with the group velocity of the laser pulse times the electric field strength of the vector potential of the laser pulse driving the bubble. So this is what it looks like. The laser pulse here drives the traveling along at its group velocity, will drive the structure. And this, so the question is, how can the laser pulse drive away the electrons? Well, it's really just the light pressure here that does this. And it means that local electrons, which are locally oscillating in the field of the laser pulse, tend to be pushed away from regions of high intensity because they are oscillating in a gradient of a field. And that means their restoring force in the oscillation period will be always less than on the lower side of the field than on the higher side of the field. So particles will tend to zigzag out of the region of high intensity. That's called the ponderomotive force. And the other thing is the vector potential. We use a normalized version of the vector potential of the laser field. It's just normalized relative to the momentum of the particle, the rest energy of the electron, and as I mentioned to you, the group velocity, the Lorentz factor of the group velocity is just proportional to the ratio of the frequencies. Because the plasma frequency is inversely proportional, is proportional to the square root of the plasma density. You see that the Lorentz factor here is proportional to the ratio of the square root of the densities, of the so-called critical density, which is the density at which the light will not propagate in the plasma. Anyway, but the main point here is that the velocity of the particle, of the laser pulse, is always less than the velocity of the particle that's being accelerated. So you can see here that it gives you a way, because of this dependence on the density of the particle. So the maximum energy of the particle, this Lorentz factor, is really the energy of the particle, is proportional to the electric field, the potential, and inversely proportional to the wavelength squared, and also inversely proportional to the density of the plasma. So that means that if you want to tune these accelerators, one can either vary the intensity of the laser pulse, or the density, or the wavelength. So this shows you, these are experiments that have been carried out, which shows you that you can get to a wide range of energies just by changing the density of the accelerator, density of the plasma, the wavelength of the laser beam, the green, which shows you what happens when you go to 10 microns. It has 800 nanometers, and if you change the intensity, you can also tune it in this across this band here. Anyway, that means that you have a tunable laser. And the maximum energy that people have already got to is about nearly 10 GeV. So that's for a conventional accelerator, you're talking about hundreds of meters of accelerator. So so the other interesting property of these accelerators is that you can control the injection of the accelerator into the plasma. You don't need an external accelerator particle to put in. You can actually inject short particles into the accelerating structure from the background plasma. And in this case, what we've done is we've shown that you can do it using a plasma density bump. So we use a very small plasma density bump. That changes because the group velocity of and the phase velocity of the laser pulse in the plasma depends on the plasma density. You can see you can change the velocity of the. In this case, I call it phase velocity here because it's phase velocity of the bubble itself. But it means that you can change the velocity of the bubble, and this means that particles that are forming the sheath of the accelerating structure will find their way into the bubble by changing the velocity. So a very small number of particles which are streaming around the outside of the particle will be injected into the particle. So in this case, you can inject even down to attosecond bunches. So you can inject bunches which are very, very short, much, much shorter than you can get with a conventional accelerator. So this is all we've done. So started some work experimentally on this. This is theoretical work that we've done. So we can see by tuning the size of this density bump, you can tune the bunch length. So in this case, this is the length here, we measured in microns, and there's an associated charge with the bunch. So by injecting more electrons in for a longer time, you can inject more charge. So you can then tune you can tune the parameters of the accelerator. So you can tune them from several femtoseconds down to several attoseconds, or several hundreds of attoseconds. So this shows you here that we can get to about 260 attoseconds bunch length, which is very short. And the peak current of these, because it's very short and you have quite a lot of charge, you can have very high peak currents of the order of 10 kiloamperes. So, so what I'm going to show you now is a simulation. So a lot of the work we do in planning our experiments is through simulations. We have models which model the electromagnetic radiation propagation, and also the interaction of the charged particles with the electrostatic and electromagnetic fields. So this is called particle and cell simulations. And what I'm going to show you now is a simulation of the back of a bubble. And the reason why I'm showing you this, I want to show you a few features which may come as a bit of a surprise. First of all, one is the injection of extremely short electron bunches into the back of the bubble. So I'm only going to show you the very back of the bubble. The very back of the bubble has been marked with this dotted white line. The dotted white line. And you'll see, and the color code here on the right-hand side, color code only particles which are above an energy of about 5 MeV. I'm going to only show you particles which have gained enough energy. You'll see here, you'll see some particles gain energy and they accelerate inside the bubble, and some particles gain energy and stay outside the bubble. They don't get to as high of energy, but you produce a lot of particles in that way. So you'll see now in the simulation now, this is the back. You see here, you form the back of there's the back of the bubble blown up, and these particles here, you see that some particles that are streaming around the back of the bubble have gained enough energy. They gain energy of above about a few MeV here, and some particles have been trapped inside the bubble. So what we've done here, we've used a 10% bump to get force injection here, and you can see these electrons here are a few MeV, and these electrons that are injected are up to a few hundreds of MeV. And these carry on accelerating, and they're very, very short bunches. So these are bunches which are of the order of about 300 attoseconds in duration. So you can see here, these bunches are growing in energy as they accelerate. They don't move very fast. This window that I'm showing you here travels along at the speed of light. So you can see these particles will drift back ever so slightly, but they will gain energy. And you see the bubble, the back of the bubble is drifting backwards, and that's because the velocity of the bubble is quite a bit less than the speed of light compared with electrons. So you can see the electrons are drifting forward, the back of the bubble is drifting backwards. And eventually these electrons will get to the middle of the bubble and they'll outrun the accelerating rate. But it shows you that now we can control these electron bunches and we can produce very short electron bunches, and these can have quite good properties. So, and these electrons that are streaming around the side, these are electrons which one wouldn't normally bother, but these electrons actually come out as a coherent beam, which I'll show you later. So, so most of the experiments that we've done have been done on the Alpha X project at Strathclyde, where we had a laser of a few 30 to 40 terawatts, 1 joule and 30 femtoseconds, and we focused it to a small spot in gas or a capillary, and we accelerate these particles. And all the equipment that you see around there, it's equipment to measure the properties of the electrons that are being produced, and also to guide the electrons. So, for example, these are magnets here, which we use to guide the electrons, and we're looking at applying these by putting them through an undulator. This is a set of permanent magnets which cause the electrons to undulate periodically. And we also have a bending magnet here, and the bending magnet is used to measure the energy of the particles. And we can also put in other components here to measure the transverse energy spread as well. But this shows you that we can measure all the properties of the laser pulse in our system. So I'm going to show you now that actually we have quite good properties of electron pulses. And they all depend on having a good laser. So that's one of the challenges, is getting a laser which is stable enough to be able to do these experiments. That's a very big challenge. And actually, most lasers are not really capable of producing stable laser beams. So one always has fluctuating beams. So one does these experiments, and sometimes it works, they work well, and sometimes when the laser is not working well, then things fluctuate hugely. But so what I'm going to show you is really the best that we've done. Okay. So one of the important things is the electron energy spread of the beam. So we measure these using a magnet, as I told you, a dipole magnet. And we've measured the energy spread of these beams to be much less than 1%. So this is very good, because that means that the beam is a high quality beam. So if you want to use it to drive a free electron laser, you want really the smallest energy spread you can get. In fact, you want to be down to about 0.1%. So this is very promising, because it shows that it's possible to do that, to get close to 0.1%. And these are electrons of energy of about 130, 140 MeV. So if you want to use a free electron laser, you normally accelerate them up to GeV. And that means that if you can preserve the absolute energy spread of 600 kilovolts, because of course this is the relative energy spread here, if you can preserve that up to GeV, then one gets a relative energy spread less than 0.1%. So this would be suitable for a free electron laser. The other thing is the stability of the energy. So this central bit of the energy, whether it stays from shot to shot, it remains at the same energy. So what we've done is, when the laser's been working very well, we've been able to show that the beams are very, very stable to within about 2 or 3%. So that means that you can use them for experiments. So we have used them for experiments. The other thing is the pointing stability. Now, of course, you want the electrons to go in the same direction. Now, because the fields in the accelerator are very large, there can be a tendency for the pointing to fluctuate. But what I'm showing you here is that if you have a very stable laser beam or the appropriate accelerating plasma, for example, a capillary, one can have the stability, the pointing stability of around 1 milliradian, or even less than 1 milliradian. This is about half a milliradian here. That means that you can start thinking about transporting the beam. So we use permanent magnets here. These are our permanent magnets. These act as magnetic lenses. That allows you to transport the beam over a long length. So another important property of the electrons that you produce in these accelerators is called the emittance. Emittance is the analog of the wavelength of light. It gives you the focusability of light. So if you have a very short wavelength of light, you will have a very focusable light. You can focus to a very small spot. So, and actually in plasma, this is the emittance. That means if you have a very low emittance or a small emittance, then you can focus to a very small spot. And what that really means in practice is that the transverse momenta of particles in the electron beam is small, the range of transverse momenta of the particles. And that means that they don't spread out, because if you have a large transverse momentum spread, it means that the electrons will diverge very quickly, you see. So this parameter called the emittance tells you that the beam is not spread out, basically. And if you think about it in terms of light, it means that if you have a short wavelength of light, it doesn't diffract very strongly. It's the same sort of principle in a way. Anyway, these are measurements we've done. We use small holes in a mask here, and we dice the beam up into different beamlets, and each beamlet corresponds to a different transverse momentum group of electrons. And then you can then calculate the area of you can calculate the area of this distribution here, and that tells you basically that you have a small spread. The other thing is the bunch length. As I told you in the other slides, is that you can produce electron bunches which are down to attoseconds. So So what we've done, we've measured these electron bunches, and we measure something called coherent transition radiation. We sometimes call this CTR. This is radiation normally occurring in the infrared or the terahertz range, frequency range. When a short electron bunch, high energy short electron bunch, passes through a thin foil, it excites radiation from the foil, which then has a spectrum which mimics the spectrum of the electron bunch distribution. So by measuring the spectrum of the light, you can infer the electron bunch length. And so this, what I'm showing you here, this is coherent transition radiation. I won't go into the physics of it. We don't have time. But what it means is that by measuring the spectrum here, one can, if you have very much shorter wavelengths, a spectrum which goes to very much shorter wavelengths, what that means is that you have Fourier components of the electron bunch, which are short wavelength Fourier components. That means the bunch must be short. Okay. So what this shows here, by measuring the spectrum, you'll be able to show that the electron bunch is about 1 femtosecond in duration. So that's very good because no other accelerators can produce these type of very short bunches easily. And in fact, if you go below 1 femtosecond, almost there are no other type of accelerators which can do it. So I mentioned to you, these are just simulations that if you go to longer wavelengths, oh, maybe I should mention also that the charge in the electron bunch is of the order of a few picocoulomb, okay? But if you go to longer wavelengths, so use a laser, let's say 10 microns, this is a CO2 wavelength, in low density plasma, so you can use a plasma density of less than 10 to the 17 electrons per cubic centimeter, one can then produce electrons. These are very preliminary simulations, but that means what we show here is to go to a very low density, we can produce very high charge beams. And we can produce electrons very efficiently from the plasma, and we can produce of the order of 30 nanocoulombs of charge, up at around a few hundred MeV, and that means about 3 joules of energy in the electron beam, the high energy electron beam. So this is just simulation. It just shows you that when you study this area, one also looks at parameters, maybe the lasers one doesn't have at the moment, but maybe build some new lasers to investigate these things. So if you want a commercial device, you really do need to go down this route. So, but producing high charge with a low laser pulse is just one way of doing it. But as I showed you in my simulation before, with electrons that are not trapped, these so-called side electrons. So the laser beam comes in and it goes through the plasma and it emits a beam which is emitted at about 45 degrees, 30 to 40 degrees, and it can carry a lot of charge. In fact, the charge that's pushed away by the laser pulse, a large fraction of it comes out of these electron beams, these side electron beams. So you can produce electrons in range between 1 and 10 MeV, these side electrons. These are not like the high energy electrons, the high quality ones that I showed you. These are larger energy spread beams, 5 or 10%. And you can produce charges, you can extract charges, convert the laser pulse into a charged beam with about 5 or 10 nanocoulombs. In fact, we've already done some experiments that shows that we can produce up to 500 nanocoulombs, maybe even a microcoulomb. So that's quite extraordinary because that means that the peak current in these beams can be of the order of many tens of kiloamperes. Okay. And so we're looking at using these for pulse radiolysis. These can be used directly also to produce terahertz radiation with millijoule energy. So these are useful and interesting beams that one would normally neglect and not think about. In fact, it's quite curious. These are what the beams look like. So these are foils that we use to detect the beam, and they come out at 45 degrees. So you can see that these beams look like a hollow cone, and they actually have a reasonable energy spread, about a few 10%, but a huge amount of charge. They take out a lot of energy of the laser beam, ends up in these electron beams. Now, people always wonder why their equipment surrounding these accelerators always dies. And that's because these electron beams actually hit the equipment, or they again, so my connection is slightly unstable. So, and you can produce single cycle pulses. So you can see at the bottom right-hand side here, you could produce single cycle pulses of terahertz radiation, very broadband spectra, up to about 3 terahertz. One of the things that we are studying at Strathclyde. So you can also take these electron beams and you can pass them through an undulator. This is a periodic structure here. This periodic structure is an array of permanent magnets which deflect the electron beam from side to side, and that can produce, these are the devices that you find in synchrotron sources. You can use them to directly produce either VUV radiation, ultraviolet radiation, or X-rays. And so what we did was we demonstrated first in the visible here, where we were able to show it. This was the very first measurements that we did in 2008, which actually was quite a groundbreaking result because it showed you can use these charged particles for traditional synchrotron sources. And we've also extended this into the UV. And what's interesting here, even though you only have about 10 to the 7 photons, you have a very short pulse. So by going to shorter and shorter wavelengths, you go to shorter and shorter pulses, down to the pulse length of the electron bunch. Okay. So this shows you here that actually we can produce quite reasonable radiation using these devices. So this shows you that with the correct accelerator, the correct undulator, you can get you can make a synchrotron source. And another thing you could use it for, ultimately, if the properties of the charge of the bunch is high, up to 10 to 100 picocoulomb, and you've seen from my simulation, we can go up to several hundred picocoulomb. And if we have an energy about 1 GeV, which is quite possible, we've already demonstrated up to 1 GeV. Other people have accelerated even up to nearly 10 GeV. We can make a free electron laser. The free electron laser is exactly like a synchrotron source, except that the quality of the electron beam is so high that the feedback of the synchrotron radiation onto the electrons bunches the electrons on a very fine scale, a spatial scale, and makes the radiation coherent. So, and we can also use the accelerator itself for the undulator. So this shows you here, the laser beam makes a bubble, and the electrons get accelerated in this, and these electrons then will oscillate transversely in the bubble. In this case, we drive the transverse acceleration using the field of the laser beam, because the laser beam oscillates in the field. We get these very, very high, it's like a very high Wiggler parameter Wiggler. We produce a radiation with a critical frequency around 500 keV and photons out to around 7 MeV. And the electron bunches here are very, very short. These are very narrow energy spread, and you're talking about a few percent energy spread. And so you can start thinking about using this radiation to do things like phase contrast imaging, because it's more or less a point source. If you pass it through the X-rays through an object, the object will normally be transparent, so the contrast will be low. But if you have a very short, very point source, you can use the transverse coherence of the beam to look at the interference at a certain distance from the object. And from looking at the interference here, one can actually measure objects which have low contrast. The other thing you can think about doing is using the plasma bubble structure to use the Wiggler or the undulator, which is the bubble itself, as an ion channel free electron laser. That means you can then miniaturize the free electron laser. So in principle, you could have you can have a laser-driven accelerator followed by a plasma undulator, and you could make this type of accelerator. So what we've shown theoretically here, we're trying this experimentally, it's a It's a big challenge, but in principle, we can make this coherent in the same way as a free electron laser will be coherent. So this shows you here, and I'm going to be going on to the final part of my talk in a few minutes. But this just shows you here where we've got to and where we want to go to. So this shows you conventional sources like synchrotron sources, their range of wavelengths and the tuning range and their brightness. So this is the brilliance or the brightness. This is the number of photons per second per unit area, per unit solid angle, and per unit bandwidth. And you can see here, we've already managed to produce electromagnetic radiation that's equivalent to a third generation synchrotron source. And by extending the energy of the bin charge, we can make something which is exceeding the conventional Wiggler radiation synchrotron sources by 1 or 2 orders of magnitude in brightness, this brilliance. And if one makes it coherent, you can increase, because of course the coherence really means that you use the energy of all the particles, because every particle will contribute to the radiation field coherently. So that means that you can enhance the intensity from a synchrotron type of intensities to by just the number of particles, basically, which is, in this case, is 10 to the 7, 10 to the 8 particles. So you can increase the brilliance by 7 orders of magnitude. That's why free electron laser is interesting. And as you can see in the bottom right-hand side, you can think about using it for imaging. So these are the sort of imaging things that we've done. We can use the electrons directly for imaging here. We can use the electron beam, making bremsstrahlung for looking at dense matter. So these are dense matter measurements. And we can also use this for phase contrast imaging. So you can see here, you can see fine structure. And we've been able to show that we can go down to a resolution of around 2 microns. So the last part of my talk, I'm nearly there, is how can we use the laser pulse to amplify light? So in this case, what we do is we collide 2 laser pulses in plasma. These are 2 intense laser pulses, and 1 short pulse and 1 long pulse. And where they collide, they make a beat wave. And that beat wave has an intensity variation associated with it, which has a scale length of lambda by 2, the wavelength over 2 of the light. Okay, so this is a very, very sharp intensity gradient. So you remember I told you earlier about the ponderomotive force. The ponderomotive force is proportional to the gradient of the intensity. So this means that if you can make a very sharp gradient by having a beat wave, you can drive these particles using the ponderomotive force out of the regions of high intensity. Now, if you do this in a plasma and you choose the density correct, then you can drive it using a Raman process. Of course, the famous Indian physicist Raman showed that you could use a third wave, which was in a solid, to excite to do a sort of parametric conversion of light from one frequency to another frequency. Here we do exactly the same thing. We can use 3 waves. We can use a seed, which makes a beat wave at the position where they collide inside the plasma. And as the pump moves over the seed, then the seed will be amplified. So, and what happens here, if you use a chirp pulse, so maybe I should just remind you here about the Raman effect again. Here we have a pump pulse, okay, with that excites a plasma wave. So you tune these two, you tune this wave and the other wave, the seed wave, so that the frequency difference equals the plasma frequency. Then you can excite a Langmuir wave using this Raman process. And this Langmuir wave then will grow, and the echelon that it produces, this is a Bragg grating that it produces, will have a refractive index which follows the density of the wave. inside the plasma, and it'll scatter one of the waves into the other wave. In other words, here we scatter the pump wave into the seed wave. Okay, and as long as you satisfy the momentum and energy conservation, so the pump frequency must be equal to the seed frequency plus the plasma frequency, and similarly the momentum of the photons at the pump, the wave vector of the pump must equal to the wave vector of the seed plus the wave vector of the plasma wave. And of course, the reason why you have a wave vector here is because it's a traveling wave here, and the plasma wave is traveling through the plasma because of the frequencies are not matched. That means you don't have a stationary beat wave, you have a traveling beat wave. And if you choose a pump which is chirped, then you can produce a echelon inside the plasma, which is only localized in a small region. So it acts as a chirp pulse amplifier. So that's quite an interesting thing. So we've been able to demonstrate that in the lab. And this shows you the demonstration here, because normally the bandwidth in the Raman process is very narrow. So because it's very narrow, that means that the bunch length, the pulse length will be very long, because we'll only amplify the central parts of the laser pulse. But if you chirp it across the plasma and the laser pulse, then one can actually sample different regions in the laser pulse and amplify each Fourier component at different times. And that means basically you can amplify all the Fourier components. So you can convert it into a broadband amplifier. It's called chirp amplification. Exactly the same idea in a conventional laser. And this means that you can avoid this temporal broadening, in other words, the stretching of the pulse, and you can amplify short pulses. And you also get this, what we call super radiant scaling of the pulse. So you can use these amplifiers. And the other thing we can use it for, if we collide two equal pulses, identical pulses in plasma along with two different intensities, one pulse can amplify one part of this pulse, and the other pulse can amplify a little bit of the other pulse, and one produces both the Stokes and the anti-Stokes. And from those, you can actually, if you collide them at a single point inside the plasma here, one can then measure the local plasma density. And this just shows you here that you can you measure the density. So we've been able to measure the density over several centimeters in the plasma. So that shows you that you can also use this for a measuring tool, not just for amplifying light. And this just shows you here how the thing amplifies. These are just parts of experiments. But what's really interesting is that the gain of the medium, in other words, this is how strongly it can amplify the radiation, can be extremely high. So we can have a gain here over several millimeters, which are 8 orders of magnitude. That means that the gain length is very, very short. So for the length over which you get one order of magnitude growth in the field can be of the order of a millimeter or even less than a millimeter. So maybe a few hundred microns. So in this case, we have 8 orders of magnitude in a few centimeters. So what we've been able to show here is that we can inject peak nanojoules microjoules of energy and amplify the radiation to millijoules. So we can amplify by this huge factor. So to investigate all this physics, we've set up SCARPA, the Scottish Centre for the Application of Plasma-Based Accelerators. And so this is and something one of my colleagues is listening to this talk, Ritu Isak. He was central to setting this whole thing up many years ago. And so this is a large facility now. It contains 2 lasers, 350 terawatt laser and a 40 terawatt laser, also a kilohertz laser running sub-terawatt laser. And we use that to produce secondary radiation to study all the physics that I've been talking to you about. But also in addition to accelerating protons, ions, producing positrons, and X-rays and gamma rays. So this is really a toolkit for people to use. So this is a 1,200 square meter lab. And I'll just maybe finish off by concluding that what I've shown you is how you can take a laser pulse and excite plasma waves, use the ponderomotive force, the forces, the light pressure of the laser pulse to drive the plasma. You can either do it using a very short pulse of light or the beat wave, and that means that you can use it for an accelerator, as an undulator, production of electromagnetic radiation. You can do it quite efficiently. You can produce these low energy electron beams with very high efficiency, and the high energy electron beams lower efficiency. But and in terms of using it as an amplifier, you can then use the plasma as an amplifier. So you could convert. So the amplifier is basically a way of converting one energy source into another energy source. So you can take a long pulse and you can convert it into a short pulse, so thereby amplifying a short pulse. And you can study lots and lots of things. The applications that we're investigating: radiobiology, ultra-fast probing, high-resolution imaging, radioisotope productions, detector development, radiation damage testing, and the list is endless, because basically it's a very powerful tool for researchers. And with that, I'd like to conclude and thank you very much for patiently listening. And I'm now ready for questions, and thank you very much.
Thank you, sir, for enlightening us with your knowledge. The session was really very informative. Now, welcome participants to the question and answer session. Let's march on this session. Now, I request Dr. Sanjeev Goyal and Dr. Poonam C. Kumar to attend the audience for question and answer session.
Thank you, Dino sir, for very informative lecture. There were lots of comments in the appreciation in the chat box. Lecture was full of beautiful slides, which made the easy to understand this subject. The lecture was so well covered that there is hardly any question. Even then, there is one question from Samim Akhtar, who is asking that, is there any tool available for simulation? Is there any tool available for simulation?
Tool for what? Sorry, I didn't get that. Dr. Goyal.
Excuse me, Professor Dino.
Is there any? I didn't get. There was interference just at the point you.
Any tool available for simulation?
Simulation.
Yes, sir.
Oh yes, there are many tools for simulation. So we use several codes for that. We use a code called B.Tech. We use a code. Other codes, Osiris, for example.
No.
And there's a code called epoch. So these are particle and cell codes. Generally, we use those because you need to track the particles individually. And they use quite a heavy computing resources to do these things, because you need to run them for days on a supercomputer. So the simulations that I showed you, some of them run for days, some of them even weeks on a supercomputer. So that's basically, and you need to use these tools because it's.
Sir, I have a question.
Yes.
Is there any other question?
Sir, I have one question.
Yes,
Sir.
please.
Sanjeev sir.
Yes, ma'am.
Can we ask Professor Dino to stop sharing his screen because we can't see the participants?
Okay, very good. Sorry about that.
It's no problem, sir. There was a hand raised by Mr. Pratap Kumar. Mr. Pratap Kumar, are you still there? You can ask your question.
Yes, madam.
Okay, please ask your question.
Sir, myself Pratap sir from Bangalore, Christ University, pursuing PhD, sir, in mechanical engineering. My topic is on welding technology, sir. So how it's related with laser plasma technology, sir? Interactions with
Okay.
we can use like XRD, any material characterization, sir?
Yeah, you can use it because basically you can produce X-rays for XRD or fluorescence studies or whatever diffraction fluorescence studies, etc. And you can use pump and probe. These pulses of radiation, X-rays, you can easily produce X-rays in the normal synchrotron range up to 100 kV, no problem. You can then use those for X-ray diffraction, for example. You have enough photons to use them for X-ray diffraction. The pulse is very short, so if you want to do pump probe studies, you can then, because it's synchronized with the laser, as long as you have another source which is synchronized with the laser, then you can use that for the pumping part of it. So, for example, one thing you could do is use the laser pulse to damage the medium, and then look at the recovery or the change in the properties. Or you can use a particle beam. So, for example, you can produce an ion beam or a proton beam and use that to damage material, and then look at the response to the material. Or you can
one more.
Or you can compress the medium using a laser pulse, for example, and then look at the time evolution. So you have a very powerful tool.
Okay, sir. How it is like it is a destructive or non-destructive testing, sir?
Non-destructive testing, you can do that. Yes, you've got X-rays, you can do that. So if you want to use X-rays, just in the same way as you use X-rays in a synchrotron source, you can do everything you want with a synchrotron source, with a laser-driven source. The only difference...
Sir, also any job opportunity, sir, after completing PhD or material science subject?
Yeah, you can get jobs with it as well. That's possible. So the science can yield jobs. It can yield good science. Yeah, absolutely.
Okay, sir. Because I already completed some course on non-destructive testing, sir. Magnetic particle inspection, ultrasonic inspection, radiography, dye penetrant.
So we have a project called Panama. And Panama is a project where we're looking using X-ray diffraction, X-ray fluorescence, and all similar things to study materials for the nuclear industry. Because one of the problems with the nuclear industry is that these power stations have been around for a long time under heavy radiation damage in harsh environment, and one needs to study these things. So actually we're just building a new beamline called Panama to do exactly that. So if you're interested in that, send me an email and I can tell you about that. It's a very interesting project because it's directed specifically to the nuclear industry, nuclear sector, for examining materials in relevant to the nuclear industry. For example, insulation in high radiation areas, or parts of the actual.
Okay, sir. Sir, you are testing. I am doing one more DST, Department of Science and Technology project, sir, on civil construction materials. So any powder also, it is possible to extract the characterization of that material, sir?
Yeah.
Or only metal, only mechanical related materials, or construction material like cement?
Yeah, cement. In fact,
some other industrial waste powder, sir.
Yeah, part of Panama. So we're doing imaging. We're doing looking at the materials.
Yeah, is that possible to characterize that? That concrete materials or some mud and other industrial waste material powders.
Exactly, because whatever you can do with a synchrotron, you can do it with a laser-driven source. So I think there's no. You can use a if you can do the experiments using a synchrotron, you can do it with a source, with a laser-driven source. So one of the things we're looking at is macroscopic imaging, large object imaging, but with very high resolution. Because if you can then, so maybe that's for concrete, that's an interesting thing because you could look at the structure of concrete.
There are two more.
Do a tomographic image of concrete structure, for example.
Thank you, sir.
Thank you. We have another question from Alka Mehta. Alka Mehta, if you're there, we have unmuted yourself. Please ask your question.
Hello, Professor Dino. This is Alka Mehta from Professor Nitikant's lab.
Yes, I remember meeting you, Alka. Yes. So, yes, your question?
Alka, we can't hear you.
Alka ma'am, please unmute.
We can't hear you.
Hello?
Yeah, go ahead, Alka.
Sir, actually, I want to ask you that there is still a position for postdoc student in the field of terahertz radiation in your laboratory?
Well, at this time, there's nothing really, and I'm getting new grants in about a couple of months. So at that time, maybe some new opportunities will arise.
Okay. Okay.
So you should just keep in touch.
Okay. Yeah, sure. Thank you so much.
Okay.
Dr. Pavan, are you online? Dr. Pavan Kumar.
Yes. Hello.
Hello. Yes. Audible. Yes. Go ahead.
My question is that many recently I've seen a paper. What is the effect of the magnetic field on the Raman amplification? Because upper hybrid resonance also will take place. What is the effect of upper hybrid resonance on the Raman amplification?
Well, in our case, because the problem with Raman amplification, the big challenge is wave breaking.
Yeah.
Now that limits the efficiency of that. So actually, we studying not so much the Raman case, because even if when you use a magnetic field, you can't get around the wave breaking problems. So what we do is we're looking at the two-wave process, which is the Compton regime. Now this is the analog of the free electron laser. Now, if you have a high enough intensity, then the bunching of the particles, the formation of the echelon is dominated by the ponderomotive force rather than the plasma Langmuir wave. Okay, it's not a resonant effect. And that means that you can tune it away from the Raman resonance, and you can get. So we've been able to measure. We've actually done some experiments which we've shown the Compton regime, that it works. We still don't know whether it'll be efficient, and I think it's still a big challenge because people have been working on this for many years.
Yeah.
And it's still challenging. And I think to add a magnetic field will, it's very hard to experimentally to add these things into the systems because these are very challenging experiments.
Yes. And next question is that in which area we will more focus at here at our institute? In which area? Because I did the work in like light matter interaction, basically plasma, solid, basically plasma and solids. Here we started some works with my colleagues, like at basically we are more focused on the radiation generation.
Yeah, sure.
Yes, but in which area?
I think it's worthwhile focusing on radiation generation because, at the end, if you think about it, the accelerator itself is not really useful, except if you use it for producing radiation. So, there are uses for particle physics and so on, but that's the energy is way higher than we can produce. But for the range of energies we produce, the best use of the accelerator is actually to produce electromagnetic radiation. So that's why I focus on terahertz radiation, the ultraviolet radiation production, and X-ray, maybe gamma rays as well. So if one can make the advantage of producing gamma ray directly from the plasma using this resonant Beatetron motion, is that you don't intercept the beam with anything. So you have a very clean source. You just have a gas and a laser beam, and that's it.
Okay. So
my recommendation is just to continue concentrating, and as you know, we're collaborating anyway on these things.
Yeah. Yes.
It's just a question of making sure the collaboration proceeds properly with the people with busy schedules. So you need to push the agenda there.
Okay, thank you, Professor Dino.
Pleasure, Malan. And thank you very much for arranging me to come to give this talk, by the way.
I think there are no questions. Sanjeev, Dr. Sanjeev, do you have any questions? From my side, there are no questions.
No, ma'am. No further question.
Over to you, Nina. Dr. Nina, over to you.
Thank you, ma'am. Thank you, sir. Now we would be ending question and answer session. Thank you, sir, for taking the queries and solve them with facts and figures. Thank you, sir. Now, I would like to request Dr. Poonam C. Kumar, HOD Applied Sciences and Humanities and convener of this international webinar series, to give the concluding remark and vote of thanks. Ma'am, please.
Thank you, Dr. Neena. Am I audible?
Yes, ma'am, you are audible.
Thank you very much, Professor Dino Jaroszynski. Good evening, all the dignitaries and participants. It's my pleasure to present before you the summary of the entire webinar series. The international webinar series organized by the Department of Applied Science and Humanities of RKGIT started on 4th August with its inaugural lecture by Dr. D.K. Aswal, Director of National Physical Laboratory, New Delhi, on the Aswal model of inclusive growth. The lecture was attended by more than 700 viewers simultaneously on Zoom, YouTube, and Facebook. The second lecture was on 7th August by Professor Rajiv Petathil, head of the Rutherford Appleton Laboratory, United Kingdom, on the subject Next Generation High Power Laser Technology. The third lecture was on Photonics Revolution by Professor Anurag Sharma from IIT Delhi on 12th August. Fourth lecture of the webinar series was on 18th August by duo professors Dr. K.K. Pandey and Dr. S.R. Shukla, both scientists G at the Institute of Wood Science and Technology, Bangalore. They had spoken in detail about the introduction and application of nanotechnology in the wood products. The fifth and the last lecture of the international webinar series by Professor Dino Jaroszynski just concluded. He enlightened us about the new technologies based on laser plasma interactions. The viewer list is continuously increasing on YouTube and Facebook for all the lectures. Now, I express our gratitude to all the speakers who spared the valuable time to share the knowledge with us and to the participants from all over the globe. We express our gratitude to the team members that we could manage such a webinar series, which was not less than a flower vase consisting of selected fragrance flowers from different parts of the world. My heartfelt thanks to the management of our institute, the directors, the deans for supporting in all ways during the entire webinar series. Special mention to the technical team, Mr. Jatin Gupta, Mr. Santosh Mishra, Dr. Sanjay Singh, Dr. Vikas Katoj, Dr. Amit Sharma, Mr. Hitesh, who were behind the scene throughout. I would also like to acknowledge our anchoring team, Dr. Garima Garg, Dr. Neena Sharma, Dr. Ritu Sharma, and our media person, Mr. Pavan Pandey, for the good media coverage, and all the other members who contributed directly or indirectly in the success of the webinar series. Before I conclude, my special thanks to the coordinators and invitation team of the webinar series, Dr. Sanjeev Goel, Dr. Pavan Kumar, and Dr. Parag Singhal, who were continuously working for the success of the program. Without their support, the program would have not been possible. And I want to thank each and every member of my department who may not be directly involved, but supported in all the possible ways they could by silently carrying out their assigned duties. Thank you, everyone. Thank you so much. It was a pleasure working with you all. Thank you, Professor Dino, once again. Thank you, everyone. And before we conclude, all the dignitaries and the organizing team members and the department team, faculty, they all should switch on the videos so that we can take a photograph. And once the photograph is taken, please let us know. All the organizing team, technical team, dignitaries, department faculty, please switch on your video so that a photograph can be taken. Can somebody tell me if it is done?
Ma'am, it's done from my side.
Okay. Okay. Thank you, Dr. Neena. And over to you now for the end of the session.
Thank you, ma'am. The feedback link has been shared in chat box, and after filling the link, your certificate would be shared on the registered mail ID. Thank you very much.
Now, if anybody wants to talk to Professor Dino in the informal way, they can. We can unmute themselves and.
Ma'am, let's clap for the success of this event.
Yes, let's cancel. Let's do the virtual clap.
Okay, virtual.
Thank you, everyone.
Thank you. Thank you very much.
Thank you, sir.
Hope to see you in physical, sir. This was virtual.
Yes,
Let's hope
yes,
we'll
definitely
meet
do that.
again. Yeah.
Thank you very much.
Any plans to come in near future?
Thank you very much.
Okay,
Thank
sir.
you. And thanks to everybody for listening patiently and asking questions.
Thank you, sir. Thank you so much.
Thank you so much. It was a pleasure, sir. Thank you.
Okay.
So we'll be on for 10-15 minutes for the feedback link. And those who fill the feedback, they can leave the session.
गोयल सर, हेलो
हेलो, हाँ बोलो कौन जी?
सर क्वेश्चन पूछ सकते हैं, पूछो कुछ सर जिसमें कर सकते हैं काम।
हाँ पूछिए ना।
आप पूछिए ना सर, आप भी तो अपनी तरफ से, मैंने तो पूछ लिया, आप भी पूछ सर। आप भी तो फिजिक्स के, कोई भी ऐसा इंटरडिसिप्लिनरी रेस है या जिसमें सारे मिलके काम कर सकते हैं, ऐसा नहीं है कि वो तो चलो सर मेरा अपना था। आप भी पूछिए सर। गोयल सर,
Doesn't matter. You can think and ask later.
Okay.
You can discuss. Where is Mr. Vikas Katoch? If you have any.
Dr. Katoch, Dr. Katoch, Dr. Vikas Katoch.
No, there is no question right now. He's saying that he will ask later on.
You can ask later on. You can think about the topics and discuss in person later on other medium. Okay, Professor Dino, thank you so much. We'll take leave now. Okay.
Thank you, sir. Thank you so much.
Okay, thank you. अब कर रहे हैं सर, कितनी देर हो गई? अभी तो मैंने उनको हटा, देखें वो है क्या? अभी यूं चलेगा ना, पूछ लेते हैं उनसे, लेकिन कह देंगे इज लेफ्ट, हम एक ही से खड़े पे वेट कर रहे हैं। कर दिया?
Thank you, madam, for successful event, madam. सही होगी आपकी event.
Sir, hold on, sir. एक minute. We can talk later. There is one Miss Dr. Sanjay Upadhyay. He raised hand very late, so we can ask his question. We can ask his question. We'll just unmute him. But Professor Dino has already left.
Yes, ma'am.
Or we gave so much of time. There was a time gap also. Anybody could have asked questions. अच्छा हो नहीं रहा है?